Welcome to ShowOffer.io. We are here to up-level your interview performances and help you land your dream offers. My name is Tony, and I'm a technical coach on ShowOffer platform. In today's video, we're going to walk you through with how to design Slack. And this is the frequently asked interview questions for OpenAI and Meta. Now, at the very beginning of this video, please quiz yourself. Here are several questions that might be asked during your interview questions when designing Slack. Question number 1, how would you ensure strict message ordering in group chats? What about multi-clients? Question number 2, how would you design real-time communications? Question number 3, how would you allow users to delete messages? Question number 4, how would you scale your infrastructure to handle users frequently going online and offline? If you think you are not familiar with those questions and answers, please follow us. So this video will bring you the answers and also the open discussions to see the trade-offs. And also there might be an upgraded challenge, how to design ChatGPT-like app. So in our today's video, we have 5 chapters. Chapter number 1 is the requirement side. So in requirements part chapter, we have functional requirements and non-functional requirements. The second part is entities and APIs. So basically we'll illustrate what kind of the object we want to store and what kind of a high-level APIs should be passed. The third part is the high-level design. It's actually using the building blocks and the data schema of the entities to illustrate each of the functional requirements one by one. And the fourth part is the deep dives. So basically, this is typical for the staff level or engineering manager level. They must have 2 to 3 topics to deep dive to improve the performance of the system based on high scalability. And last but not least is the recap part. And in our today's video, we're going to use these challenging questions as our guide to see how we can surface the problem and solve them with the system level. If you like our channel, please subscribe, like our video, and leave any comments. We would like to discuss with you and also learn from you. Let's start off today's content. So let's begin with the functional requirements. Functional requirements means, for example, if this is an app that a lot of users using that, or say it's a 2C app, basically the functional requirements means what users should do or what users can do. So let's start. For Slack, I think the first one is the user can send and receive messages in one-on-one chat or group chats. So basically there's a prerequisite, which is the user can bounding each other from the one-on-one or setting up the group chats. I think those are kind of pretty straightforward, so we don't need to talk too much about that. But the thing is how you can send messages and receive messages in both one-on-one and one-to-group or group-to-one. This is usually the scenario. So I want to just highlight that we can mainly talk about the group chat case. The reason is the one-on-one chat in Slack is actually one special scenario. If you understand how the group chats happens, one-on-one is just a simpler case. For the second functional requirements, I would say, during your sending the messages, users can send rich media like the images, videos, files, links, etc. as part of the message or just a single message. So this is very easy to understand because we always do the things, right? Okay, function requirement number 3. Users can receive real-time notification for new messages, right? We are building a chat system. The low latency or say the real-time notifications for both online, offline, this is super, super important. It's not like sending the emails and we do some async like that. But here's the cases. Some of the user or the recipients, they can be online at that moment when receiving the message. So it would be straightforward to using some of the communication protocols to support those the real-time sendings. But what about the offline users? So they are not connecting to our communication protocols. What would be the way that we can support sending those kind of notifications to let them know, and then they can click on the notification and back online to see the full messages and history? So this is the functional requirements we need to satisfy. Functional requirement number 4. Users can delete their own messages from a chat. So if you frequently use Slack, you can see that you can edit the message, and more importantly, if you send something wrong, you can delete the message. So this is a basic functions. But from the recipient side, if the user is online he can see those messages has been sent to his app and then it's disappeared from the front end side when triggered a deleting message. But what about the offline users? How would it interact with the backend infrastructure to make sure those messages will not appear here as never sent? So this is the fourth functional requirements. You may hear about like something like the status of the typing a message and read receipt, and those are kind of signals that can be tracked as a functional requirements. But I think usually the case during your interviews, those four functional requirements are more top level, and for the read receipt or status change, those are kind of the trigger signals that can put below the line. After the functional requirements, let's come to the second part, which is the non-functional requirements, NFRs. Non-functional requirements means how the system could support, especially to some of the extreme scenarios. The first non-functional requirement would be high scalability. And we suppose that 1 billion monthly active users and over 100K concurrent chats. So here's a pro tip during your interviews. We highly suggest every non-functional requirement can come up with some metrics that can be quantifiable measured. So this is a very good signal, especially for the step class level, because it can show how good you're familiar and how you measure the success of a system, especially the high scale. The second non-functional requirement is low latency. Because this is a chat system, we do want to support the real-time chats, especially for those online users. For example, the metric here we say is 95 percentile of the end-to-end delivery is around 200 milliseconds. You may want to ask, what is the magic number of 200 milliseconds? So low latency messaging system isn't about benchmarks, it's about perceived real-timeness. Once message delivery feels delayed, trust and engaged drop fast. So in practice, like under 200 milliseconds means real time for the real cases. And it's going to be a bonus if you can say that we would fall back to degraded fan out or batch sense at 500 milliseconds load. If there's a heavy load, if you want to improve the throughputs, that's really a good signal that you've seen in the real life. So the third non-functional requirement here is a discussion about the CAP theorem. We are aware messaging guarantees, so we prioritize the availability from the system level. But we do want to enforce strong per chat message orderings. So here's a pro tip here. How should we answer such questions for non-functional requirement regarding the CAP theorem? I think a good signal is how you philosophically to see how the CAP theorem applies. At a high level of the system, we definitely want to have a very high availability of the system without any, the broken issues and user behavior issues. But to some of the functional levels, especially like the group chats and the considering about the orderings, how we can truncate case by case for the consistency to support as strong as possible the consistency, especially in the ordering part. I think this is not a contradict, right? From the high level, we want to keep the availability, and from the functional level, how we can make it as consistent as possible. So the fourth non-functional requirement we will say is message durability, which means there is zero acknowledged message that should be lost. The illustration here is if a user hits send and then immediately loses internet, the message must still exist when they reconnect. And here comes up very interesting discussion point or the pro tips. Do you know when is it safe to delete a message? So I would say there comes up with like two special cases. The first one is the sender explicitly delete a message, which we support for the functional requirement number 4. The second scenario is the system enforces a retention policy, which means that, for example, such as like an auto deletion after 30 days, for example, for compliance or storage limits. I think from the interview perspective, for the staff class engineers or engineering managers, you should treat durability and deletion as two separate concerns. You never assume delivery means it's safe to re-erase. Now let's come to the fifth non-functional requirement, which is the multi-device in sync. Basically, if we want to measure the success, we want to say 95 percentile sync latency is less than 300 milliseconds, for example, or 100% inconsistency in notification, etc. So basically, the illustration here is a user might have a lot of devices as there are multiple clients, desktops, phones, tablets. Basically, how we can make sure that those messages are in sync without any duplications or without any missings. So during the interview, I think the multi-client sync is kind of a silent interview killer. For the interviews like the staff class level or engineering managers, if you want to stand out, I think you need to call out those edge cases, such as the session trackings per device, the idempotent event delivery, and also the consistent state propagations across all logged in clients. So these are our non-functional requirements, and those are the starting points to discuss how we can deep dive and make our system better. Now let's come to the core entities part. So there are 5 core entities we want to use in our system design. The first one, user. User is a registered participant who can chat and receive notifications. The second one is a chat. Chat is actually a channel or direct conversation with a list of members or just a one-on-one. So you can treat chat as where a conversation actually happens. And number 3 is the message. So message is an entity contains of the conversation message based on the text or the media unit sent to a chat. You may have a question. In Slack system, there is another entity called thread. So do we want to include that? I agree. A thread can be treated as a message of messages because these are the replies to a specific message. But in our today's video, we just want to use a message because the only extension column of the thread compared to the message is going to be a parent message ID to link to that specific message. Number 4 is the media. So media is actually the asset linked to a message. Can be image, can be video, or can be any other files. Number 5 is the device session. Device session means an active WebSocket or push notification endpoint for a user's device. You may have a question because some of the materials mentioned about the clients and what is the difference between this one and the device session because they look similar. So a client can be a platform. For example, iOS, Android, or web browser, etc. A user can have multiple clients. For device session, yes, user can have multiple device sessions as well, because it is actually describe active trackable connections in the real-time communication. So in our today's video, the table schema we use is device session. And roughly, we can treat the clients for your better understanding in the high-level design part. Now let's come to the part about API and the communication protocol, WebSocket. Basically, this is a chat system. So communication protocol in TCP/IP layer is super important. So there's going to be a special part among the system design like design Slack or WhatsApp. But in other system design questions, you won't cover this part from the communication protocols. So in terms of that, let's discuss what are the commonly used communication protocols and why we use WebSocket. So usually the case in our the common scenarios, there are 3 cases. The first one is called HTTP polling. So the client repeatedly asks the server, is there any new messages? And simply, this is a very simple mechanism, but it's very inefficient because it introduces latency and an unnecessary load. The second one is HTTP long polling, which is on top of the HTTP polling, there's a refinement so that the server holds the request open until there's new data. It is more efficient compared to the HTTP polling, but still involves re-establishing the connection for each time. The third protocol that we are using today is WebSocket. And there's almost no other judgments that usually the case we use WebSocket because it is a persistent and a full duplex TCP connection that allows both server and client to push data at any time. It is ideal for like the low latency bi-directional communication, and this is the standards. So let's see if we want to clarify what are the WebSocket beneficials for the Slack-like system. So it can reduce latency, as we mentioned. There's no need to reconnect or pull. It enables live typing, read receipts, message delivery in real time. Those are the status updates. And those are kind of the WebSocket events that we support. And third one is it supports multiple concurrent sessions per users. For example, like the desktop or mobile apps, things like that. So in terms of that, we know that we're going to use WebSocket based on the comparisons and basic understandings. So you might wonder, what are the WebSocket supportive events as we mentioned here? So I'll give you a screenshot from our website. This is an article that we've written in ShowOffer.io. If you have any interest, you can take a look and to see how the WebSocket looks like. So basically in our system design today, 3 core events types that are supported from all the events. For example, the send a message, which is from the WebSocket client to the WebSocket server, that the user sends a message to a chat, which is a channel. The second event type we support is a new message. So when server receive any new send messages or delete messages, for example, it forwards a new message to the client, for the WebSocket client, and it fan out of the messages to all the participants. And the third one, as I mentioned, this is a message deleted. So message deleted is one other new event type, and this can also be triggered from the server, the WebSocket server, to the WebSocket clients. And it notifies when the message is deleted to the WebSocket client side. You may have a question, right? We just mentioned about the clients, and we're also thinking about device sessions. You may ask, hey, why are you still talking about clients? So this client here is totally different from what we discussed. So this is the WebSocket client to support the communication protocols in the TCP layer. And if you want to know more about how the WebSocket looks like and how this can be supported from the details, and also with the example, like how the send message look like from the client side and this WebSocket server side, you can move to our website to see a very detailed example. And I don't want to spend too much time onto the details, but you need to have a clear idea like why we use WebSocket and what is their advantages in real-time chatting. Now let's come to the parts about high-level design. So high-level design is very important to interpret the architecture of the functional requirements into each of the workflow. So in our today's high-level design, I'm going to walk you through all the 4 functional requirements into 4 workflows with the building blocks to connect, the data schema to expand our entities, and how the data flows should be looks like based on the request and response. I believe in most of the materials, you don't see that too much details of the steps, but in our ShowOffer.io platform, we definitely want to make sure that each of the functional requirements is illustrated detailed to make sure you understand what's going on from the processing parts. I want to let you be aware in this section we assume 2 parts. One thing is we assume all the users from the recipient side are active. For the offline users to receive messages, we will cover in the functional requirement number 3 in the high-level design part shortly. The second assumption is we use group chat, which means one sender to many receivers, as the example in the diagram. The reason is that the participants in receiver side, one-on-one chat is a specific scenario that will be covered by the group chats, which means the number of the recipients reduced from many to 1, which is the only change in the new message sent from the WebSocket servers back to the clients. So let's start from the functional requirement number 1. When the user already has a chat to send or a channel to send, the client A denotes as the user A to send a message. Here's the message example. The payload could be Hey Team as a content, and the chat ID is noted as a chat123. The message will be first sent to the API gateway, and the gateway will do the authentication, check for the rate limiting, and also route to the correct server, which is the chat server here. There's no horizontally scaled servers. For the chat server side, it can do a couple of things. First thing is they validate the chat type and check with the user belongings, like which channel it should belong to, if it's correct or not. The second thing is it generates a message ID and also the timestamp to the message, and this is kind of a records to log that specific message into the database. And then the third step is insert into the database into the table called message, which is keyed by the message ID, and it has the chat ID, sender ID, and also content, If this is a thread message, it should have some parent message ID as well, but this is optional. We don't want to discuss more. And the final one is when the message is being created. Also, optionally, in the deep dive parts, we're gonna introduce like a sequence ID per chat for the ordering, but this will be covered later. So in our DB, other than the message table as a fact table, we also have some dim tables like the user from the user ID and the username, the chats, which is for a specific chat ID, is this a group or not, or it is when it is created as an entity. And also a very important one, this is a connection map, which is the chat members table. And for each of the chat ID, how many or what is the user IDs listed there and when are they joined. So this is a keep up to date. So you can see there's a one chat ID maps to one or many user IDs in that table. After the records of the message has been persisted inside the DB, the chat server talked to the WebSocket server to do two things. One thing is they query all the active device sessions or all the active users you can imagine for each of the participants. Because we assume that all the participants are online and we don't discuss the offline case right now, so you can check with the chat members and make sure that all the user IDs are be pulled from the chat ID, and then the WebSocket server will send this message broadcast to all the recipients inside the chat members table. So as you can see, the message has been broadcasted to the client or the user B, the online parts, and the user C, who is also on the online parts. So this is the end of the whole workflow for the functional requirement number 1. There's also one thing we want to note a little bit. We didn't discuss more on how the group is created or how the users can be added into the existing group. So this is a pretty straightforward operations. We don't want to spend much time on that. You can try answer yourself and be aware of the table insertion in the database. Now let's come to the second workflow for the functional requirement number 2, when users can send rich media files like images, videos, or any other files. So we denote the whole workflow based on the functional requirement number 1, and then we make changes to adding the colors of the orange colors for the functional requirement number 2. For example, the message sent can be the event is also the send message, but the payload not only the chat ID, the contents, but also a media ID, which is generated by the server, which is the media 456. Let's see how it goes. First of all, the client A user send the upload media request to the media server as we added here. So the media server does several things. First of all, it validates the file type at the size, and then it returns a pre-assigned URL to upload to the blob storage. We use Amazon AWS S3 here. And then we also preserve a media ID where I already noted here in the message set. So the pre-assigned URL along with the media ID will send back to the client A, and then client A will directly upload using the pre-assigned URL to S3 from their client side. Once it's successfully uploaded, the media URL will be generated after the success upload and returned back to the client A. And then it triggers the actual message sent with the media URL or media ID to the gateway, which is the similar one as the functional requirement number 1 to send a message. So it passes with the media ID and media URL to the chat server, and similar things happens to a functional requirement number 1. It will persist the records into the DB with the message, but here you will generate 2 new columns. One is for the media URL, one is for the media ID. And similarly, the chat server will figure out the WebSocket server to talk to him like, please pass this message to the online recipient. One is from the user B, one is from the user C with the media ID and the media URL. And this message will be broadcasted to them. Now let's come to the functional requirement number 3, where users can receive real-time notifications for new messages. So this can be truncated into 2 scenarios. One is for the online users with the real-time WebSocket communication. The second case is, of course, the offline users, when there needs to be a push notification services that support this function. So before we jump into the high-level design on the functional requirement number 3, we need to understand 2 sets of concepts. The first set of concept is what is offline versus online in the ChatApp. So a user is considered to be online if they have an active WebSocket connection to the chat system, typically via an open app tab, background mobile session, or desktop client. A user is offline when no active device sessions are tracked, meaning no open WebSocket connection exists. So from the descriptions, you can see the device session is very important to be added inside offline or online check status. The second set of the concept is push notification for the offline user is not equal to the message delivery. So if you map to the step-by-step from the message sent to when push notification has been sent to the offline user and then the offline user back online, there can be 5 steps. The first step is the message has been sent and the backend persisted in the database and prepares the delivery. So if this user is offline, there's no delivery yet. And then the user is still offline and the backend sends the push notification while like the AP ends. And so it is still not delivered, but the notification just sent. So here is the notification is shown on the client side as third step, and the user sees a banner or lock screen message, and only the notification has been arrived. There's no interaction with the offline user to be back online and to see the message and read the message. And then comes to the user taps and opens the app, the WebSocket connection is re-established. So this is actually the starting points of the message delivery. And then the message is synced across all the clients. The message is pulled and replayed from the inbox, where we'll denote later, and it is now delivered when the user actually sees the message. Now, after we understand the 2 key sets of the concepts, I think we can move to the high-level design for the functional requirement number 3. So I know that most of the materials doesn't illustrate that details of the step-by-step, but this is our ShowOffer platform try to do to make you understand what is exact step-by-step here. So I may slow down a little bit to make sure every step you are familiar with. And also for the some of the steps, same as the previous ones, we can skip them as fast as possible. So functional number 3, we still use the blue color to notate the different parts. And also we're using the solid lines, same as before as the online cases, and also the dashed lines for the offline cases, as you can see here. And also from the client B, we suppose he is offline right now and the client C is online right now from the recipient parts. So the first step is the same. The client sends the message via WebSocket. This is the same forwarded to the gateway, and gateway doing the second step as the same to redirect to the chat server. For the chat server, it first validates the chat members and also get a list of the participants from the database. This is also the same. But step number 4 is a little bit different. So basically, they need to get active sessions from the device session, which is a new table created here by the list. So in the device session table, it has the status, which can be active or inactive, and also with the new column called last heartbeat to check if this device session is still alive or not, based on the acceptable threshold, maybe 1 minute, maybe 30 seconds, to make sure it is not closed or shut down by the user intentionally. So this is a new table, device sessions, as we mentioned. And then the message, similarly from the previous steps, it will be persisted into the database. A new record will be inserted into the message, and this table is the message ID, chat ID, sender ID, and content, similar as the media as well. And for the step 6, this is a new step because for the offline users, we need to make sure that this message will be replayed later once they back online. So there's a new table called inbox. So each entry contains the user ID, the message ID, and created at, and also an optional delivered at timestamp once it is delivered. So after this part, number 7 is only for the online cases. For the online users, there is a real-time fan out from the WebSocket server to the online users. And the rest of them is actually similar, but the thing is we want to make sure that each find out a new message event to all connected clients based on their WebSocket connection ID in the device session tables, which we recorded here. Because basically, the WebSocket is not sticky to a specific client or users. So you actually need to make sure where is the WebSocket server located at. This is a very sophisticated part, but we need to note it here on the high-level design part. And then we comes to the number 8, where the offline user is not there. We should have a push notification server or the APN as a part to support a registered push token. So the chat server triggers a notification through the push notification server. And this is only a notification and does not mark the message as delivered. So this kind of a push notification will be pushed into the client B, who is offline. So step number 9 is when the client B goes back online, and the WebSocket server will query the inbox right? This is here to query this user ID and all the message IDs and replay. So because the user B is online and you will reconnect and also mark all the messages to be delivered as delivered at a specific timestamp. And then the inbox will be cleared out by retention policy or triggered by the cron jobs in step 10. So in this case, the message in the inbox can be managed, and also the message that needs to be sent to the offline user when back online has been accomplished. Now let's come to the functional requirement number 4, when user can delete their sending messages. So here's an example of the message. The event type changed to delete message, and the payload here is message ID, the chat ID, right? The message ID notate which message he wants to delete. So here comes to the pink color for functional requirement number 4, and we go step by step. The first step, similarly, the client sends the delete message request. The process begins with the sender, or say the client A, initiate the message deletion from the chat UI. The client emits a delete message WebSocket event containing the message ID and the chat ID in the payload. This request is routed through the gateway, just like the send message, and forwarded to the appropriate chat server instance here. So the second step from the gateway is actually the identifications, real limiting, and route. So this is the similar thing, we just skipped there. From the chat server side, it authorizes and soft delete the message. Upon receiving the request, the chat server first validates that if the message exists and that the requesting user is indeed the original sender, it queries the message table by the message ID and check if the sender ID equals the user ID who requested. If the check passes, the chat server updates the message row to mark it as deleted as a new column here. So this is actually implemented as a soft delete by adding this new column with the default value false to the message table and then setting it to be true. And the next step is the chat server find out to the online participants. So at this part is similar that the chat server queries the chat members tables to identify all the participants of the chat, and it then cross-references the device sessions table to determine which participants are currently online. For those who active WebSocket connections, a message deleted events is immediately sent to like the client C here, as we denoted. So let's come to the client B who is offline. So this is kind of tricky. I might going a little bit deeper. So the web servers generates a inbox records for the offline users. For the chat members who are offline, the WebSocket server inserts an entry in the inbox table for each message that needs to be delivered later, as we noted in the previous function number 3. So each row contains the user ID, message ID, and delivered equals to false, inserted at, and to be deleted as false. So here we need to have one new column is to be deleted. Yeah. So if the sender deletes a message while some recipient is still offline, the system checks whether it has already been delivered to each user. So if the message was never delivered, to be delivered equals to false, the corresponding inbox row is either deleted or skipped. So no message deleted events is sent to the client. The recipient will never know that message existed. Only messages that were previously delivered will emit a message deleted events when deleted. And step number 6 is from the online parts, the UI parts. So the deleted message is omitted from the scroll back queries, the online users only. The deletion is visually enforced by excluding the message with is deleted equals to true in any message list query. When offline clients come back online, like we said, the deleted message will be filtered out entirely, appearing as if never existed. So basically, that is the high-level design from the functional requirement number 1 to number 4, which we believe that all the functional requirements can be satisfied even though this is not scaled or not optimized, which we can discuss later in the deep dives. But after that, I think there should be a data schema summary. So I also screenshot all the data schema summary written on our website, www.showoffer.io, in this question. So if you want to see more details about the write-ups, you can visit there. And also, there might be another interesting topic to discuss about what database selection should be. So here's my answer. For a Slack-like chat system, the ideal primary database should be balancing strong consistency, write throughput, and query flexibility. A relational database like MySQL or PostgreSQL is a strong fit for core entities like users, messages, chats, and chat members due to its support for the ACID transactions, structured joins, and predictable indexing. However, at scale, with billions of messages and thousands of concurrent writes, a vanilla SQL database may struggle to scale horizontally. So this is why practically many production systems, including Slack, adopts Vetis, a sharding middleware that allows you to horizontally scale your MySQL while preserving SQL semantics. On the other hand, while a relational database is a strong default by structured messaging workloads, NoSQL options like Amazon DynamoDB can also power a Slack-like system, especially when optimizing for scale and availability. DynamoDB offers single-digit millisecond latency, auto-scaling throughput, and built-in high availability, making it ideal for storing denormalized messages, records, inboxes, or device sessions. For example, messages can be stored using a composite key, chat ID plus created at, to ensure ordered access per chat, and the DynamoDB streams can power final pipelines to WebSocket servers. However, trade-offs include weaker consistency guarantees, lack of flexible joins, and more complex schema evolution, which may require designing around eventual consistency and data duplications. So in the interviews, great system design answers don't just pick a tech stack, they explain the trade-offs. Instead of saying I'd use MySQL or I'd use DynamoDB, top candidates can speak something to compare their pros and cons, like I did. Now let's start with deep dive number 1, how to keep group chat message ordering at scale. So where does this problem surface in our design, and why this is going to be a challenging problem that we ask ahead of today's video? So in our high-level design, messages flow from the client to gateway to chat server to WebSocket server to devices, and then these messages are stored centrally in the message table. In the group chat scenarios, many users may send messages nearly simultaneously from different devices, networks, and regions. So if there's no strict ordering mechanism, there will be a confuse. For example, if user A in a group chat sends "let's meet at 5 p.m." and at the same time user B replies "sounds good" in the same chat, depending on the delivery race conditions, these messages could appear out of order on different user devices, disrupting the conversational flow and creating confusions in those chats. So our goal is to figure out the best solutions to mitigate this issue. So at a high level, there are 3 different options or methodologies. The first one is client-side timestamp. So in this approach, the client attaches a timestamp when sending a message, and then the server simply stores and uses that for the ordering. While this may seem straightforward and simple, right, it introduces significant risk in distributed multi-device scenarios. User devices often have unsynchronized clocks, leading to inconsistent ordering across clients. And meanwhile, malicious or buggy clients could manipulate timestamps to reorder the conversation. So this option is too fragile to support strong consistency expectations in real-time chat. The second option, which is the server-side sequence number per chat. So here, the chat server maintains an atomic per chat counter that increments with each new messages. Each message is assigned a unique, monotonically increasing sequence number during the ingestion and persisted in the message table. So all queries, rendering, and read, resets, etc. uses this sequence for the deterministic order. And this guarantees the correct ordering even with the concurrent multi-device sends. But the downside here is that atomic increments can become a bottleneck at a very high scale, unless each chat is strictly routed to a single partition or server sharded. And still, for many media scale systems, this option is good because it balances the correctness with implementation simplicity. In our today's recommendation, we definitely want you to use Kafka-based ordered ingestion per chat. And this design routes all the incoming messages through Kafka, mapping each the chat to a specific Kafka partition using a consistent hashing of the chat ID, for example. Kafka natively enforces strict message ordering per partition, so concurrent sends across devices are correctly serialized. A customer service reads from each partition, assigns a sequence number, and writes the message into the database in order. And this architecture scales horizontally because as chats grows, more partitions can be added. So the only cons that we can think about is it introduces infrastructure complexity for the whole system. But above all, based on the trade-off discussions, we apply option 3 here in our high-level design. In our deep dive number 1. After we're discussing about the options and we select the Kafka-based solution, and we come back to our diagram to see how we can add the flow into our high-level design. So right now, this is the deep dive number 1, and we use the brown color to distinguish with the colors previously. Right now, we are adding a new component, which is Kafka, and it uses for the topic partition by the chat ID. It stores the message in partition and then preserves the per chat message order by the sequence number. What it does here is actually they have the Kafka consumers, maybe Kafka consumer 1, 2, till n, and each of the Kafka consumers has a dedicated Kafka consumer reads message by the partition. And each of them assign a monotonic sequence number, as we mentioned, and writes to the database here. And correspondingly, after we have the database change feed, where triggers the find out services, we can also add a group of workers, which is called the find out workers, which they are working as fetching the chat members, look up the device sessions to check their online status, pushed via the WebSocket for the online users, and also persistent inbox for the offline users when they come back and they replay that. So all the rest process are the same. So this is our deep dive number 1, where we can solve the problem of the group chat ordering. But have you ever thought about what is the potential problem or challenges here? Yes, you may know that. There might be a celebrity chat problem. When Kafka partitions are based on the chat ID, ultra-active chats like all hands or town hall channels can cause a hot partition, where one Kafka partition and its consumer get overwhelmed while others stay idle. So how to resolve this problem? I pause it here, but I don't want to give you the answer for now. If you want to have the answers, please refer to our ShowOffer.io platform, and we write our answer there. But it's good for you to think about how to resolve this question, because it can be a pretty generic question when you apply for Kafka or other scalability solutions. Now let's come to deep dive number 2, scalability of WebSocket infrastructure and active session lookup. So how this problem happens from the high scalability sides. At a moderate scale, it is feasible to have this chat server or final worker query a centralized device session table or in-memory cache like Redis to discover where users are connected. But at a scale of 100 million concurrent WebSocket sessions, even doing lookups or broadcasting to the right subsets becomes expensive. So there are 3 core scalability issues emerge. Number 1, active session populate, which means you cannot do DB queries for every message just to find out which device is online. Bottleneck number 2, churn from user. Connect, disconnect creates delivery uncertainty. As users rapidly go online, offline across devices or networks, ensuring correct find out and avoiding duplicate or missed message becomes difficult at scale. Bottleneck number 3, which is the backend storage pressure, which is the DB write or read load. High message throughput plus real-time reads can overwhelm underlying database unless optimize the caching, denormalization, or async processing. And in this chapter, we'll break this down. Now let's come to the first bottleneck, active sessions populate. If we think about 100 million plus concurrent users, the challenge is not just querying where the user is. It's about how WebSocket servers can efficiently populate and manage the active session data in real time without overloading Redis. So to avoid this, we recommend shifting to a PubSub find out model. So what is a PubSub? In short, PubSub is a messaging pattern where senders or publishers send messages to name the channels, which is topics, without needing to know the receivers. Receivers, as subscribers, listen to specific topics and automatically receive any new messages published to them. And this system decouples the producers and the consumers, making it ideal for real-time find out, scalability, and dynamic subscribers. With that said, let's see how it works. So the details are in the diagram, but it has four changes. First of all, it has the message published once. which means the find out workers publish to the message, like the chat channel. The second one is the selective subscription. So each WebSocket server subscribes only to channels needed for its currently the connected users, avoiding the global broadcasts. Number 3, there's a local filtering and also the delivery. Once a message arrives on the subscribed channel, the WebSocket server uses as a local session map to forward it to the correct user connection. There's no Redis or DB lookup required. And number 4, this is offline handling. Users who are not connected will not receive this message from the server. Their delivery falls back to the inbox updates and push notification, which has been illustrated. So here, deep dive number 2 for the first bottleneck solutions, we add a Redis pub/sub system, and we add the final workers to publish those message to the chat channel, which is the chat ID partitioned to the public service, and from the WebSocket servers at the subscriber side to subscribe the chat channel, which is based on the chat ID. Now let's come to the bottleneck number 2, where WebSocket server churn and the users moving between the nodes. Even with the recommended solutions above in our current design in Deep Dive 2, each WebSocket server dynamically subscribes to the Redis pub/sub channels like chat channel, which keyed by the chat ID. Based on the chat room its connected user participating in. But if the user churns, you get some issues. First of all, the stale subscriptions. The old WebSocket server is still subscribed to the channels for a user, but it no longer owns. It has the missed unnecessary find out. Redis may still push messages to the old WebSocket server, wasting network and compute. It also can introduce the race conditions, like during the rapid reconnects, both the old and the new servers may subscribe at the same time. So our goal here is to ensure only one WebSocket server is subscribed to a given user chat channel, the one currently serving that user, and the update is dynamically to the user moves. So basically there are 2 options that we can think about. Option number 1 is we can always subscribe to all chat channels on connection. Yeah, this is very simple and brute force, but it is really wasteful find out. And it can also risk of the duplicate messages unless clients are deduped. There's a second option which we recommended here is a list-based session ownership with the Redis TTL. So let's come back to the design diagram where we added here. So this we added here based on the previous design. So this approach also uses the Redis to coordinate with the WebSocket server, which owns the user session at any given time. When the user connects, the WebSocket server sets a key like user ID equals to WebSocket ID with a short TTL, for example, 10 seconds. And we extend it periodically with a heartbeat, which is the P expire here. Only if a server holds the valid lease does it subscribe to the user's chat channel, for example, keyed by the chat ID. This guarantees only one WebSocket server is responsible for the delivery per user, avoiding the duplicates and reducing find out overhead. However, it requires more infrastructure coordination, handling the edge cases like lease expiration or reconnected races, but it pays off in cleaner scalability and efficiency at a very large scale. Let's come back to here. Here I ask a question, like what is the exact workflow and now when the user A drops and then back online? How is the WebSocket server moves? So I'll cover this in a very brief answer, but you can jump into the ShowOffer.io platform to see our article. There's a detailed design. So this is a step-by-step flow. First of all, let's see if the user A moves between the WebSocket servers. The first step is initiation. So user A connects to WebSocket server WebSocket 1, and WebSocket server 1 sets a Redis key, let's say user A equals to WebSocket 1, and expire 10 seconds. WebSocket 1 then subscribes to all the channels based on the chat ID where A is in. And the heartbeat set like the P expire extends to at least every few seconds, like 10 seconds. And then it is an expected disconnect, maybe the network drop. So at this moment, WebSocket 1 stops receiving the heartbeat from user A, and after TTL like 10 seconds, the lease in Redis expires, and WebSocket 1 can safely unsubscribe from the chat channels or simply ignore incoming messages. And step 3 is when user A reconnect via the new WebSocket server, and this This time, it established the WebSocket connection route to WebSocket server 2. And this server 2 tries to set leads like user A with the WebSocket server 2 with the new expiration 10 seconds. And then WebSocket server 2 now becomes the session owner, and it subscribes to channels where user A came from, like chat IDs. And then the message delivery resumes. For instance, Redis pops up only delivers message to WebSocket server 2, and WebSocket server 2 sends new message to user A without duplications. And there's no wasted fine out to WebSocket server 1 as it no longer holds the leads. Now let's come to the bottleneck number 3, the backend storage pressure, especially for the DB read and write load. So there are two primary stress points. For the hybrid write through to the throughput to the messages and the inbox tables, every chat message triggers an inbox write for n recipients. So this is a high scalability. The second primary stress point is there's a high read amplification for chat metadata and user session state. For example, you need to check with the chat members, device sessions, lookups, etc. So for our strategy side, we want to have a combination of the two strategies. Strategy number 1, which is we want to horizontally partition of the message and inbox table. And strategy number 2, which is to read optimize the caching for hot metadata and final paths. Let's come to the our diagram to illustrate. So in this chapter, we can see that all the servers we are horizontally scaled. That because those are stateless, and we can partition by the consistent hashing from the chat server and WebSocket server. From the database side, as we mentioned, it can be DB sharding by user ID or chat ID for those dim tables. And also, there should be some cache, like the Redis-based with the TTL and the eviction policy, that those cached with the heavy read metadata. For example, the chat members, the inbox, and also the device session tables. So we can set up the strategy for their evictions and make the heavy read records to be stored in the Redis cache. Now let's come to the third deep dive topic, multi-device management. And this is also the challenging question we asked you ahead of this video. In modern messaging platform, it's common the user to be logged in on multiple devices simultaneously, iPhone, laptop, tablet. So this creates a new class of the delivery and the consistency challenge. So our system must ensure that all the active devices receive real-time delivery, and devices stay in sync with message state. And the disconnected sessions receive reliable replay when reconnecting. And also we should avoid duplicated fan out or missing messages. So in this case, we have a proposal for the solution because previously we are based on each of the user. So right now we should be based on each of the device as a device or say session registry, because every user can have multiple ones. We should make the granularity more smaller. And then we also need to think about how the inbox replay can be happens to make the in-sync state and also avoid of the duplicates. Let's check about our diagram. We denote our deep dive 3 with the purple color and in several steps. So here, basically the device connects is our first step. When a user device connects to the WebSocket server, it is registered as a session by writing device session with the user ID, device ID, and assigned with a WebSocket connection. So typically this can be stored in Redis or in-memory maps. So basically when a new message is delivered while a pops up, to the WebSocket server looks up all the active sessions for the recipient users, and it sends the message to each connected device, which is the online part. And for the offline fallback here, if the device is not connected, the message is still stored in the inbox table, and it's keyed by the user ID as well as the device ID. And this ensures this message is queued for delivery when that device comes back online. And then when the device reconnects, upon the reconnection, the server checks the inbox that specific user ID and device ID and delivers that all the missed messages without any to be deleted or without any delivered. So after the successful delivery, the entries are cleared and marked as delivered here based on our cleanup jobs. So this is basically our strategy with the per device setup as well as the inbox replay. There might be an interesting part is, this is a bonus point. You may be asked like how the client-side message deduplication logic can be added, because some of the candidates may not consider about this part. So basically, if the multi-device setup, the same user might receive the same message twice, once via the WebSocket on one device, and again via an inbox replay on another device after reconnecting. So without deduplication, the results in a duplicated message or any confusing message has the history that you don't know what is the latest one, and there's no consistency in the sync. So how it works? Basically, we think that every message carries a global unique message ID and assigned in the ingestion part. And each client maintains a local cache for the recent received message IDs. For example, maybe 1,000 entries. On message receive, if message ID is new, then we render and store. And then if already seen, we skip render and silently drop. So basically, there's a pseudocode logic for comparison on the sequence number of that message, as well as the local max sequence number to illustrate that. So this ensures the consistent user experience across reconnects, devices, and delivery path without relying on perfect backend deduplications. So here's our recap and today's final thoughts. Designing a Slack-like chat system goes far beyond just sending and storing messages. It is about architecting a real-time, distributed, resilient messaging backbone that can support massive concurrency and device diversity, and all while keeping latency low and user experience seamless. In this video, we walk through every major building block, from creating chats, managing group members, to sending rich media, storing messages, and triggering WebSocket or push notifications. More importantly, we explore deep dive design trade-offs that help you answer the 4 of the toughest system design challenges often brought up in your interviews. First of all, messaging ordering in group chats. We use Kafka-based ingestion and per chat sequence number to enforce a canonical timeline for all messages, ensuring consistent rendering even when messages are sent concurrently from distributed devices. Number 2, the real-time notification at 100 million scale. We design online and offline find-out mechanism using WebSocket and inbox tables, and built-in notification delivery through the Redis PubSub and fallback logic for offline users, without overloading the backend. Number 3, deletion propagation with retention guarantees. We build an audit-compliant deletion flow that respects sender-side deletion, ensures correct client updates across devices, and prevents resurfacing or deleted contents via inbox filtering or replay rules. And number 4, WebSocket churn or multi-device reconnects at scale. We tackle infrastructure churn by introducing session leasing with Redis TTL, a PubSub-based find-out by that channel, and client-side deduplication to handle reconnect storms, which ensuring a clean handoff and the minimal duplication where users rapidly connect from the multiple locations. Altogether, these answers formed a backbone of a resilient, scalable chat infrastructure. Each challenge covered with trade-offs between the consistency, scalability, latency, and complexity, and our deep dives laid out concrete, production-ready solutions for each. You want to know more about ShowOffer.io and what ShowOffer.io can help you? So here's the final summary. We included all the callouts and open-ended design prompts throughout this write-up and video, and is perfectly for self-practice or interview discussion. If you would like to receive the feedback or want to walk through the system design in a mock interview setting, book a session with us on ShowOffer.io. And moreover, right now, we just launched a new function to book a session with the author as well. We are here to help you sharpen your skills, gain your confidence, and land your next big offers. If you like our today's video, please subscribe us, like our video, and leave your comments. Thank you, and good luck to your next interviews.